Hello everyone and welcome back to NotesNaka. Today our question is possible bipartition. So we are given a set of n people and we have to split them in two groups and the groups can be of any size such that the person who do not like each other don't end up in same group. This is the same question as is a bipartite graph possible for a given edge matrix. So the dislike like pairs A comma B given are similar to the edges given in a bipartite graph example, and we have to return if a bipartite graph is possible or not. So, so as we can see here, we are moving on to the next example. Here n is equal to 4 and the dislikes are is given as 1 comma 2, 1 comma 3 and 2 comma 4. So 1 comma 2, 1 comma 3 and 2 comma 4. So we first put values in graph. For 1 we put in 2 and 3. For 2 we put in 1 and 4. For 3 we put in 1 and for 4 we put in 2. This is the neighbors of all these nodes, and so we move on to coloring. We first start with 1 and we basically, like for example, color it blue. Then the same function is called for both of its neighbors, and if they don't already exist in the map, like when one was color blue, this relation was added into map. Then 2 and for 3 we do the same and these two are added into the map. Then again when 4 is called, when 2 is being called, its neighbor 4 is called, and for 4 we take the complementary color of 2, that is blue. So we see that we can split the graph into colors blue and green, where no neighbor of blue is green and no neighbor of green is blue. Moving on to the next example, we can see that here the number of nodes are 5 and this is the dislike or the edge array, and it is intuitive that seeing a cycle, it is not possible to bipartite this graph. So let's check if our code agrees with our intuition or not. We add to the graph the neighbors. For 1 we add 2 and 5. For 2 we add 1 and 3. For 3 we add 2 and 4. For 4 we add 3 and 5, and for 5 we add 1 and 4. So we start off with 1. 1 is initially blue, and then we call it for both of its neighbors. So 2 becomes green and 5 becomes green. Then we call it for 4 and 3, as they both are neighbors of 2 and 5. So 4 becomes blue, and as 2 calls 3, 3 also has to be blue. But when 4 calls 3, it needs it to be green. This is not possible, hence we return false. We start off by initializing a vector, a 2D vector graph, and a map. The graph is to hold all the neighbors of a given node, and the map holds the color which is associated with every node. Here, the color helps us to identify whether a number, uh, whether a node is in the first group or the second group, as we have to divide this graph into two groups. So, moving on, we initialize the graph vector by pushing row vector, and then we add neighbors for all the nodes, as you can see in the code, and then we check for each node from 1 to n if it exists in the colored graph or not, and if its neighboring nodes are all the opposite colors. So we return false it is if the conditions are not met, and return true if for all the nodes in the graph each has a different color from all its neighbors, hence not belonging to the same graph, its neighbors or the person that this person dislikes belong to the same group. Then we move on to the DFS function. In the DFS function, if the node is not present in the color map, we add it to this map, and if it is already present, the DFS function returns if its value is the color associated with it or not. If it's not true, we'll just return false. And then we check for every one of its neighbors. So the neighbors should have C XOR 1, that is the color opposite to C, and if it's not true, a biparallel graph is not possible, and if it's true, we return true, as in the graph is possible and this node doesn't cause any problem in doing so.